Forks and Dynaforks in Stroboscope. It is often necessary to make decisions about the routing of resources and the sequence of activities in a simulation model. Other times, it is necessary to model the routing of resources or the start of successor activities based on a random selection process. Forks and Dynaforks can be used to model decisions and the probabilistic selection of successor nodes. They allow the modeling of situations that are very similar to the decision and chance nodes that are found in decision trees. A fork is defined by using the statement fork, followed by the name of the fork, followed by the resource type that is routed by the fork. Optionally, the statement can also take the number of the stream to use. For the figure shown here, for example, the fork could be defined by the statement fork, route hauler, hauler. Route hauler is the name of the fork, and hauler is the resource type that flows through the incoming and outgoing links of the fork. A Dynafork is defined similarly. In this case, we used the Dynafork statement, followed by the name of the fork, followed by the resource type, followed by the optional stream to use. In a similar figure, the Dynafork route hauler can be defined by the statement a Dynafork route hauler, hauler. Notice that the obvious difference between a fork and a Dynafork is the shape of the node that is used. A fork node is shown as a circle with a triangle inside, whereas a Dynafork is shown as a circle with a burst of rays. The choice of outgoing links out of a fork or a Dynafork is called the resolution of the node. The resolution of a fork or a Dynafork occurs after the before-end actions of the terminating activity have been performed and after the current instance count of the terminating activity has been decremented. For example, in the figure above, the resolution of route hauler occurs after the before-end actions of the terminating load have been performed. Also, the resolution of route hauler occurs after the instance count of load has been decremented. A fork and a Dynafork choose their outgoing links differently. A fork is resolved exactly once for each terminating activity instance, for example, load. In the example above, it determines the routing of all haulers released by the terminating instance of load. When an instance of load ends, and before it releases any resources, it sends a message to fork route hauler to select an outgoing link, HL3, HL4, or HL5, one of the three, and then to send a message to the successor node to get in context. If the successor node is a normal activity like haul to A, then haul to A will create an instance. If the successor node is a queue like hauler's wait to fuel, then the queue simply awaits the delivery of resources. This process ensures that when the terminating instance of load starts releasing haulers through link HL2, there will be a receiving node at the other end, either an instance of haul to A or an instance of haul to B or the queue. When the fork route hauler receives a message from the terminating instance of load, It does probabilistic sampling among the outgoing links HL3, HL4, and HL5 and determines one of the three to activate. It then sends a message along that link to the node that follows, which can be normal activity hold to A, or normal activity hold to B, or the queue, to get in context to receive resources. If the succeeding node to be activated is a normal activity, then the normal activity will create an instance. Notice that every time an instance of activity load ends, at most one instance will be created, either hold to A or hold to B, and sometimes neither activity will create an instance because the link selected will be HL5. After the fork route hauler selects an outgoing link, there is a clear path for the hauler resources to follow when they are released by the terminating instance of activity load. The mechanism by which a fork route hauler will select one of the three outgoing branches is based on the strengths of those three branches, HL3, HL4, and HL5. The strength of a link is determined by the strength statement that will be described shortly. If no strength statement appears, then each link has the default strength of 1. Route hauler will add the strengths of all outgoing links, in this case HL3, HL4, and HL5, and will divide the strength of each link by the sum of the three strengths. This will give the probability of selecting each one of the three links. If two or more of the outgoing links have a strength greater than 0, then the selection process is probabilistic. If only one of the outgoing links has a strength greater than 0, then the selection process is deterministic. A decision will be made. The link to be chosen is the link whose strength is greater than 0, whereas the links that have strengths equal to 0 will not be selected. Every time an instance of load terminates, it sends a message to the fork route hauler, which then does a probabilistic process to select the successor node through links HL3, HL4, and HL5 before the terminating instance of load releases any resources of any type. This way, a fork activates only one of its successor nodes. The one destination node that is activated in this manner is the one that will receive all the resources of that type that are released by the terminating instance of load. In contrast, a DYNAFORK allows each resource that is released by a terminating activity instance to choose its own destination node. It is important to remember here that a terminating activity instance releases its characterized resources serially, one at a time. So if a terminating instance of load contains multiple haulers, they will be released one at a time through link HL2. Each hauler released by a terminating instance of activity load will reach the DYNAFORK route hauler and will make its own separate decision as to where to go next, through links HL3, HL4, or HL5. As a result, a DYNAFORK does not know ahead of time the destination node to be chosen by each resource released. Because of this, a DYNAFORK activates all its successor nodes before any resources are released through the DYNAFORK. For example, before load releases any haulers, route hauler will activate and create new instances of both normal activities, hold to A and hold to B. These instances are now ready to receive the haulers routed by the DYNAFORK route hauler. Notice that it is possible that an instance of hole 2A or hole 2B will not receive any haulers routed by route hauler. If, for example, there is only one hauler in a terminating instance of activity load, then clearly that hauler can only go to an instance of hole 2A or to an instance of hole 2B or to the queue hauler's wait to fuel. If the hauler goes to the queue hauler's wait to fuel, then the instance of hole 2A and the instance of hole 2B will not receive any haulers. This creates the unusual situation where we have instances of activities that are supposed to represent hauling, and yet they do not contain a hauler. The conclusion from this discussion is that Dynaforks have to be used with care. The selection of which branch to follow out of a fork or a Dynafork is determined by the strength attribute of the outgoing links. As mentioned earlier, the default strength attribute has the value 1. This can be changed with the strength statement that takes as an argument the name of the link followed by an expression that gives the strength for that link. For example, strength HL3 weight of A, where weight of A is a variable that defines the weight of selecting link HL3. We could have 3 such statements that define the strengths for links HL3, HL4, and HL5. Stroboscope will add those 3 values, weight of A, weight of B, weight of Q, and then use the sum to divide each of the weights to obtain probabilities by which each of the outgoing links will be activated. This mechanism also allows us to make decisions. For example, we may wish to haul to the dump site that has the smallest contents. Notice that activity haul to A delivers its contents to QA, and activity haul to B delivers its contents to QB. In this case, for example, we could define the strength of HL3 to be the logical expression that compares the current count of QA to the current count of QB. If the current count of QA is less than or equal to the current count of QB, the result will be 1. So the strength of HL3 will have the value 1. The opposite statement is used for the strength of link HL4. That is, it will have the value 1 if the current count of QA is greater than or equal to the current count of QB. The strength of HL5 is set to 0. That is, a hauler will never go and wait for fuel. When an instance of activity load terminates and before it releases any resources, it will send a message to route hauler to select an outgoing link. Route hauler will then evaluate the expressions for the strengths of the 3 outgoing links, and based on the defined expressions, either HL3 or HL4 will have the value 1, whereas the other will have the value 0. This way, the fork route hauler will make a decision to choose either HL3 if the contents of QA are less than the contents of QB, or to choose HL4 if the contents of QB are less than the contents of QA. Oftentimes, when working with forks, it is necessary to know if a particular node has created an instance. This can be determined by using the logical variable heteroholder.inContext. In this case, by using the variable ActivityName.inContext. This variable allows us to check if a particular successor is in context, that is, it has created an instance, before trying to access its properties. For example, suppose that we wish to show in the standard trace the number of haulers released by route hauler that end up in activities as opposed to in queues. In that case, we could write the statement onEnd load standard trace followed by a format specifier that contains the text holders are performing a whole activity and which takes as an argument a conditional expression. The conditional expression first checks to see if hold2a is in context. If it is, then it returns the value hold2a.holler.count, which gives us the number of Holler resources that are currently in the current instance of normal activity hold2a. If activity hold2a is not in context, then the if statement checks to see if activity hold2b is in context. If it is, then it returns the number of holders that are inside the instance of hold2b. Otherwise, it returns the value 0. The value 0 is returned when neither hold2a nor hold2b have an instance at the current simulation time. We shall now examine several examples that illustrate how forks and Dynaforks release resources. The first 4 examples will use forks, and the last 4 examples will use Dynaforks. In each set of 4 examples, the first 2 will use generic resources, and the last 2 will use characterized resources. This model uses generic resources of type unit. Unit queue is initialized with 1,000 units. The queue permits contains one resource of type permit. The purpose of this resource is to allow combi activity arrive to create instances one after another. The variable total units has the value 1000. The draw until logical expression for link U1 allows that link to draw until the number of draws is greater than or equal to total units, which in this case is 1000. As a result, the first instance of combi arrive will receive all 1000 units that have been initialized into unit queue. When the first instance of activity arrive terminates, it will send a message to the fork, which will then send a message to one of the outgoing links depending on their strengths. In this case, the branch strength is the default, which has the value 1, so each outgoing link has a probability of 1/3 of being selected. Through random sampling, the fork will select one of the 3 links and will send a message to the successor node to get in context. If the successor node is norm1, it will create an instance. If the successor node is Q2, it will simply await the delivery of resources. If the successor node is norm3, then it will create an instance. This way, the fork activates only one successor node. After that node has been selected, the terminating instance of activity arrive will release all 1000 units to that one successor node. As an example, consider the situation where the fork, through random sampling, selects link U5. In that case, norm1 will start 0 time, and Q1 will receive 0 units. Q2 will receive 0 units, and norm3 will start 1 time, and Q3 will receive 1000 units. The second example also uses generic resources. The difference in this example is the draw until expression for link U1. This draw until is the default, which is that the number of draws are greater than or equal to 1. When that condition is satisfied, then the drawing process ends. This means that combi arrive will be able to create 1000 instances. Each instance will receive one unit from the queue unit queue that will be eventually passed on through link U2 to the fork. Before any resources are released through link U2, the terminating instance of activity arrive will send a message to the fork to choose a succeeding node. The fork will choose one of the nodes U3, U4, U5 through a probabilistic process with equal probability. If, for example, link U3 is selected, then activity norm1 will create an instance, and the terminating instance of combi arrive will send the one unit that it holds through links U2 and U3 to the instance of norm1, which will eventually pass it on to Q1. After this, combi arrive will create a second instance, which will receive another unit from unit Q, and at its termination will pass it on through the fork. When the second instance of activity arrive terminates, it will send a message to the fork to select an outgoing link, which will again do a probabilistic selection process to select the succeeding node of where to send the resource. For example, this time it might select U5. Thus, this model will create 1000 instances of activity arrive, and each of the succeeding nodes norm1, Q2, and norm3 will be activated on average about 333 times. A possible example outcome is that norm1 could start 330 times, in which case Q1 will receive 330 units, Q2 will receive 348 units, and norm3 could start 322 times, which means Q3 will receive 322 units. This model is similar to the previous models, but uses characterized resources instead of generic resources. To make the definition of characterized resources for this model simple, we use a compound type, which is defined by the statement comp_type unit. As in the previous models, unit Q is initialized with 1000 units. The expression for the draw until for link U1 allows the link to draw all the units into the first instance of activity arrive. Thus, the first instance of activity arrive will contain 1000 units. At the end of activity arrive, it will send a message to the fork to select an outgoing link based on a random probabilistic process. For example, fork could select a link U3 as the output link. In this case, norm1 will create one instance, and after that, the terminating instance of arrive will release all 1000 units to norm1. The difference between generic resources and characterized resources is that when activity arrive terminates, it will send all generic resources as one package to the new instance of activity norm. In contrast, when the terminating activity arrive contains characterized resources, it will release them one at a time through links U2 and U3 into the new instance of activity norm. This gives Stroboscope an opportunity to read or change the properties of each characterized resource that is routed through U2 and U3 as they flow through those links. This model also uses characterized resources. It is very similar to the previous model, except that the expression for draw until now is the default, which allows link U1 to draw only one resource from the preceding Q unit Q. As a result, activity arrive will be able to create 1000 instances, each of which will contain one unit. When each instance of arrive terminates, it will send a message to fork to select one of the outgoing links probabilistically, and then it will route that unit through the fork to the successor node. Because of this, each of the successor nodes has a probability of 1/3 of being selected. This is the first of 4 models that use a dynamic fork instead of a regular fork. This model uses a generic resource called unit and initializes a unit queue with 1,000 units. The draw until for link U1 allows the first instance of combi arrive to remove all 1,000 units from the preceding queue. So in this model, we again have only one instance of activity arrive that will contain 1,000 units. When an instance of activity arrive terminates, it will send a message to the dynamic fork to get ready. The dynamic fork will then send a message to every outgoing link to the successor node to get ready. When norm1 receives this message, it will create an instance, and so will norm3. It will also create an instance. After this, the dynamic fork will send a message back to the terminating instance of activity arrive to release resources. Because the resources are generic, they will be released as one lump. The resources will arrive at the dynamic fork and will choose one of the 3 outgoing links at random. For example, they could choose link U3. In this case, activity norm1 will start 1 time and Q1 will receive 1,000 units. Q2 will receive 0 units. Norm3 will start 1 time, but Q3 will receive no units. This last observation is the difference between a fork and a DYNAFORK. In a fork, norm3 would not create an instance. In a DYNAFORK, norm3 would create an instance. This model also uses a dynamic fork and generic resources of type unit. The logical expression for draw until allows a U1 to draw one resource from the preceding queue unit queue. This is the default behavior. This means that activity arrive will be able to create 1,000 instances. Each instance will receive 1 unit from the preceding queue unit queue. A terminating instance of activity arrive will send a message to the dynamic fork, which will then send a message to norm1 and to norm3 to create instances. Then the terminating instance of activity arrive will release 1 unit, which will choose one of the 3 outgoing links and go either to norm1 or to Q2 or to norm3. The second terminating instance of activity arrive will follow a similar process. As a result, norm1 will start 1,000 times because it starts every time activity arrive ends, and norm3 will also start 1,000 times. However, the number of resources that they will receive will be approximately 1/3. For example, norm1 will receive 303 units and pass them on to Q1, Q2 will receive 352 units, and norm3 will receive 345 units that it will then pass on to Q3. This model illustrates how a dynamic fork routes characterized resources. This is perhaps the most interesting of all examples to be presented. In this example, unit Q is initialized with 1,000 characterized units, and the draw until for link 1 allows the first instance of activity arrive to receive all 1,000 units. When activity arrive terminates, it has 1,000 units to release. It will send a message to DFork to get ready, and DFork will send a message to norm1, to Q2, and to norm3 to get ready. Norm1 and norm3 will create an instance awaiting the arrival of resources. The terminating instance of arrive will then start releasing the characterized resources it holds one at a time. Each one of the 1,000 units will be released through link U2, will arrive at the Dynafork DFork, and each unit will make its own selection of one of the links U3, U4, and U5 probabilistically. As a result, each unit that is released can end up in any one of the 3 successor nodes. Thus, even though the terminating instance of activity arrive contains 1,000 units, 1/3 of those units can end up in norm 1, 1/3 to Q2, and 1/3 approximately to norm 3. This is different from generic resources, which, if there was 1,000 of them in the terminating instance of activity arrive, all 1,000 would end up in only one of the 3 successor nodes. This is because characterized resources are released one at a time, and as a result, each one can make its own choice at the Dynafork. It is important to notice that in this model, there will be only one instance of activity arrive, only one instance of activity norm 1, and only one instance of activity norm 3. Yet, each one of those instances, for norm 1 and for norm 3, will receive about 333 characterized resources. This model is similar to the one previously, with the difference that the draw until is the default, which allows link U1 to draw only one resource from unit Q. Thus, activity arrive will have 1,000 instances, with each instance containing one unit. When activity arrive ends, it will send a message to DFork that will create one instance of norm 1 and one instance of norm 3, and then it will route that one unit that it holds, which will make a choice of one of the 3 links U3, U4, and U5. The end result in this model is that activity arrive, activity norm 1, and activity norm 3 will have 1,000 instances. Yet only about 1/3 of the instances of norm 1 and the instances of norm 3 will actually contain units. Each of the Qs, Q1, Q2, and Q3, will receive approximately 1/3 of 1,000 units. The last 2 models that illustrate the use of dynamic forks with characterized resources are indeed the best examples of the use of Dynaforks in actual simulation models. In other words, dynamic forks or Dynaforks are best used to route characterized resources. These characterized resources always arrive one at a time, and each arriving characterized resource can make its own choice as to which successor node to follow. When should we use a fork, and when should we use a Dynafork? This page provides some conclusions based on the previous example models. For generic resources, a fork is usually the best choice. We should use a Dynafork only when it should start all normal activities that succeeded. For characterized resources, a fork is usually the best choice again. We should use a Dynafork only in 2 cases. When the preceding activity contains a group of characterized resources of the same type, and each one of those resources needs to decide its own destination when released. The second case is when the preceding activity contains only one characterized resource, but the termination of that activity should also start all normal activities that succeed the Dynafork. These are very useful conclusions to bear in mind when designing stroboscope models.